Today, we're going to peek behind the curtain of AWS Lambda. We're not just looking at the what, we're diving deep into the how. The incredible engineering that makes serverless a reality at a scale that is just mind-boggling. And when I say massive scale, I really, really mean it. Lambda is handling over 10 trillion invocations every single month for more than 1 million customers. Now, you didn't mishear that, 10 trillion. This isn't some niche service. It's a foundational pillar of the modern internet, operating at a level that's honestly hard to wrap your head around. I absolutely love this quote because it just nails the magic of it all. I mean, think about all the stuff it takes to run a really good service. You've got load balancing, auto-scaling, patching servers, dealing with hardware failures. It's a ton of work. Lambda takes all of that operational pain and experience and just compresses it. So you, the developer, can just focus on writing code. So this brings us to the big question for today. The promise is amazing, but how in the world does it actually work? How do you run code that isn't already sitting on a server waiting and then do it trillions of times a month? Let's crack that engineering puzzle together. Okay, so let's get into it by tracing the journey of just one single request, because this path is going to reveal the first and really the most fundamental challenge of on-demand computing. Right, so a request comes in to run your function, but since it's serverless, your code isn't just idling on a machine somewhere. It exists, sure, but it's basically just a package sitting in storage. So the system's number one job is to find a place for that code to run, and it has to do it, like, right now. And this whole process is what we call the cold start path. It happens the very first time a function runs, or maybe after it's been sitting idle for a while. Let's walk through it. First, the request hits a front end. That front end then has to ask a placement service. Hey, I need a spot to run this code. Where can I go? The placement service finds some room on a physical server, which Lambda calls a worker, and spins up a brand new, totally secure sandbox, which is really a tiny little virtual machine. Only then does the real work begin. Your code gets downloaded, the runtime spins up, your own initialization code runs, and after all that, finally, your function gets invoked. This right here, this is the central drama in the entire Lambda universe. The slow path of a cold start versus the lightning-fast path of a warm start. The whole goal, the entire game, is to make everything feel like a warm start. But to do that, for trillions of requests, you first have to build a system that can survive, well, everything falling apart all the time. You know, before you can make any system fast, you have to make it tough. You have to make it resilient. At the scale Lambda operates, things are failing constantly. The system has to be able to just shrug it off without the customer ever even knowing something went wrong. So the original system that kept track of all these sandboxes was called the Worker Manager, and it had one giant critical weak spot. It stored the location and status of every single sandbox, which ones were busy, which were idle, all of it, right in its own memory. Now that's fast, but it's also incredibly fragile. If the server running that Worker Manager crashed, poof, all of that critical state was just gone. The fix was a complete redesign called the assignment service, and it was a massive architectural shift. Instead of keeping state in fragile memory, every single change gets written to a durable distributed log. Think of it like an indestructible ledger that's copied across multiple data centers. It uses this leader/follower model, so if the main leader fails, one of the followers can instantly step up and take its place with absolutely zero data loss. This one change made the entire system fault-tolerant. Okay, so now the system is resilient. It can take a punch. But that just brings us to the next big challenge. How do you safely and efficiently run code from millions of different customers all on the same physical machines? In the early days, the solution was pretty simple. Just give each customer their own EC2 virtual machine. It was secure, yeah, but incredibly wasteful. Most of those machines were just sitting around doing nothing. The new model uses a technology called Firecracker to pack thousands of tiny, lightweight micro VMs onto a single server. And this works because all those different workloads are uncorrelated. It's super unlikely they'll all need peak power at the exact same moment. Think of it like rolling D&D dice. Rolling one die is random, but if you roll 1,000 dice, the average result is incredibly predictable. By packing thousands of functions together, the overall demand just smooths out, making the whole system way, way more efficient. And Firecracker was literally built from the ground up to solve this exact problem. It gives you the hardcore security isolation of a traditional virtual machine, but with the speed and density you'd expect from a container.
It's really the key that unlocks the ability to run millions of functions on shared hardware, both securely and cheaply.
So our system is resilient, it's secure, it's time to go back and face our original villain, the cold start. And believe me, this is where the story gets really, really cool. So we know Firecracker can spin up a micro VM almost instantly. That's great, but you still have to pay that initialization tax, downloading your code, starting up the runtime. For some languages like Java, that can take seconds. So the question became, what if we could just skip that whole part?
And the answer is an innovation called Lambda Snapstart. And honestly, this is just brilliant. When you deploy your function, Lambda actually runs that whole initialization process once, ahead of time. Then, right when it's fully warmed up and ready to go, it takes a complete snapshot of that micro VM's memory and disk state. So now, when a cold start request comes in, instead of starting from scratch, it just restores a new micro VM from that snapshot in milliseconds. It basically turns a slow compute problem into a blazing fast storage problem. And the impact is just staggering. A traditional cold start pays this huge latency penalty for initialization. With Snapstart, restoring from that image is up to 90% faster. For any application that's sensitive to latency, this is a total game changer. It pretty much eliminates the cold start problem for a whole class of applications. Okay, let's put all the pieces together. You've got resilience, you've got security, and you've got speed. All of these innovations work together to deliver on that one simple promise: just run my code. So why does this matter to you? Well, the assignment service means your functions stay up even when the hardware underneath them fails. Firecracker gives you that rock-solid security and performance, and Snapstart gives you incredible speed. The bottom line is this: behind that super simple interface, Lambda is a symphony of elegant solutions to some of the absolute hardest problems in computer science, all so you don't have to think about them. And that leaves us with one final thought to chew on. We've just walked through this incredible journey that's getting us closer and closer to making compute truly ephemeral, truly instant. So the question you have to ask is, once that's the default, once that's just how things work, what entirely new classes of problems are we going to solve next?